I'd like to introduce to you a very powerful theorem in the concept of finding moment about a point. It's called Varignon's theorem, and it states that the moment of any force is equal to the algebraic sum of the moments of the components of that force. What is this all about? Why don't we take a look at an example? Let's say I have a force which will be called force R, and I'm interested in finding the components of this force along these two yellow lines. They don't necessarily have to be orthogonal components, just any two components along any two arbitrary lines. In order to do so, I must create a parallelogram. Well, let's draw a line that is parallel to the first yellow line, and then let's draw a line that is parallel to the second yellow line. And it's clear here that the components along the two solid yellow lines are these green components, which I will call F1 and F2. Well, if we are interested in finding the moment of the resultant force, the pink force, about, let's say, point O, if we're interested in finding the measure of the tendency to rotate of the resultant force about point O, well, by definition, moment about a point is equal to r cross with F. Well, this small vector r is very rigid. It must be from the point that you are trying to take moment about to any point on the line of action of this force. We are interested in finding the moment of the resultant r about point O, so therefore this small r vector must go from point O to any point on the line of action of the resultant. There are infinitely many points, of course, on this line of action. Let's just choose one. I'd like to choose the tip of the resultant. The small r vector has to go from point O to the tip of the resultant, and that is your small r vector. The f vector is, of course, just the resultant vector. We're interested in finding the measure of the tendency to rotate of the resultant about point O. It's just the small r vector from point O to the tip of the resultant cross with the resultant vector. Well, the resultant vector may be expressed in terms of F1 and F2. If you recall vector addition, the resultant vector is equal to F1 vector plus F2 vector. Well, according to the distributive property, this may then be expressed as r cross with F1 plus r cross with F2. Well, r cross with F1, that's just the moment about point O of the component F1. R cross with F2 is just the moment about point O of the component F2. According to Varignon's theorem, the algebraic sum of the moments of the two components, in this case F1 and F2, is equal to the moment about point O of the resultant. And this is what Varignon's theorem is all about. Why don't we apply this theorem to our problem? We have a 500-pound force. We are trying to find the moment of this force about point A, the measure of the tendency to rotate of this force about point A. Why don't we get rid of everything? But before we do that, let's find the component of 500 along the x-axis and along the y-axis. Along the x-axis, well, that's just equal to 500 times 3/5. According to the sense of direction given, 3 is in the horizontal direction, and indeed we are trying to find the horizontal component of the 500-pound force, and 5 is just the hypotenuse of this triangle. How about the y component? Well, the y component is just equal to 500 times 4/5. According to the sense of direction given, 4 is in the vertical direction, and indeed we are trying to find the vertical component of the 500-pound force, and again 5 is just the hypotenuse of that right triangle. We do our calculation. 500 times 3/5 is equal to 300 pounds, and 500 times 4/5 is just 400 pounds. 300 pounds is the x component of the 500-pound force. 400 pounds is just the y component of that force. So let's get rid of everything, and let's focus on the components of the 500-pound force instead of the resultant itself. Moment about point A is a vector, and according to Varignon's theorem, it is equal to moment about point A of the 300-pound component plus moment about point A of the 400-pound component. The 300-pound component is just 300 times 36. A way to do this is to know the definition of moment is always force times distance if you don't want to use the cross product. The component is 300, that's the force, and the only perpendicular distance from the line of action of 300 to get to point A is 36 feet. That's the only perpendicular distance from the line of action of the 300-pound component to reach to point A. So 300 times 36. How about the y component? The force is 400, and the only perpendicular distance from the line of action of this 400-pound component to reach to point A is 12 feet. So therefore 400 must be multiplied by 12. 400 is the force, 12 is the distance. 300 is in the x direction, 36 is in the y direction, so therefore we're on the xy plane. 400 is along the y direction, 12 is along the x. Again, we're on the xy plane. I have established scalarly the moment about point A of these two components. Why don't we establish the sense of direction? According to the coordinate system given, positive x-axis is positive to the right, and positive y-axis is positive up. According to the orientation of these two axes, the positive z-axis is pointing out of the screen, and when you point your right thumb along the positive z direction, which is out of the screen, your forefingers will want to curl in this particular direction. Well, this particular direction is what is considered the positive moment direction. 300 times 36 and 400 times 12. How do we establish whether it's positive or negative moment? Well, a very easy way to do this is to create an imaginary circle which centers at the point you're trying to take moment about. In this case, it's point A. And you ask yourself the question, how will the 300-pound component want to rotate around my circle about point A? It's very clear that it wants to rotate clockwise. And since counterclockwise is considered as positive, therefore clockwise is then a negative moment. Therefore, I must put a negative sign in front of this first term. How about the 400-pound component? How does this 400-pound component want to rotate about point A? It wants to rotate counterclockwise, and counterclockwise is considered a positive moment direction, so therefore I must put a positive sign in front of this second term. and we do a little calculation here. This is equal to negative 6,000, and of course the unit is feet-pounds. Moment about point A is a vector, and its magnitude is equal to 6,000. Unit is feet-pounds. Since we have a negative, that just means it's opposite of our positive moment convention. Opposite of counterclockwise is, of course, clockwise. And this is exactly the result that we had calculated in our previous lecture, Scalar Method 1, not using Varignon's theorem. I'd like to re-emphasize two very important things. Number one is that a quick way to find moment is always force times distance. However, they need to be perpendicular to each other. If you don't want to use the r crossed with f or the cross product, it's as easy as finding force times distance, but they have to be perpendicular to each other. Number two is that you must establish the plane that is created by the force and the distance. The plane that is created by the force and distance. And you must point your right thumb in the direction that is in the positive axis perpendicular to that plane. Follow the direction of your forefingers. That will be the direction that is considered as positive moment direction.